Alright, I saw this yesterday, and I found it disturbingly... I found it disturbing. Okay, so he's talking about finding zeros of the Riemann zeta function. Okay, and there's this point where he's talking about imaginary exponents. Okay, and here he's saying we can think of, well, there's a periodicity to it, right? So, like e to the 0, or, yeah, e to the 0 is 1, but also e to the 2 pi I, or 2 pi I is 1, and e to the 4 pi I is 1, right? So there's a periodicity to it, right? But here he says that that periodicity of 2 pi, or 2 pi I, however you want to think of it, it's not actually 2 pi I. Huh, that's actually wrong too. It's just 2 pi, the periodicity is 2 pi. And then the I is an added unit on there, which is what's causing it to twist, because I is perpendicular to the dimension you're operating in, so when you raise to it, it's going to twist you in some direction. It's going to apply torque, basically, within the number space. Anyway, so your periodicity is 2 pi, not 2 pi I, so that's incorrect, which I just now noticed. But it's only, that periodicity is actually only 2 pi when your base is E. If you have any other base that you're raising to an imaginary power or a complex power, your periodicity won't be 2 pi. And this should be trivially obvious, because if your base is 0, it doesn't make sense. You don't get periodicity. It should just collapse and disappear. And if you're, say, you wanted to convert, so this is 2 pi radians, if you wanted to convert radians to degrees, there should be a base that allows you to do that. Okay, so I worked through it here. And this is mostly just me thinking, so if you want to look at that, there it is. I'm not going to walk through that. It's all there, probably with some weirdness that you're going to be like, why would you do it that way? But that's fine, because I got it. I got it working. So here in this video, zeta math, respect to zeta math. I'm not criticizing zeta math. I'm just saying that this one little thing seemed weird to me. So I went into Desmos and I actually graphed a few of these periods, and it's interesting. So here it's just straight lines, but he's only looking at base E. What if we moved bases? What if we moved around? What if we had a negative base? What happens? Let's look at it in Desmos, because I spent some time here graphing it all out. Oh, look, if there's negative bases, there's no periods happening. That's interesting. At 0, it collapses. It disappears, which is what I expected. Let me drop in E. Okay? So here, just like he's saying, right? So it's your period, this is 2 pi right here. So what's going to be hitting? It's going to be hitting the origin. It's going to be hitting, actually, yeah. So there's the origin. E and 0. E and 2 pi. E and 4 pi. Right? And I only did like 6 of these, right? So 6 pi, negative 2 pi, negative 4 pi, negative 6 pi, right? So this is the thing that he's saying. But what he did is he just drew these out as horizontal lines. These lines are actually correct. So now what we can do, let's convert radians to degrees. Now we should see our period being, what in the hell? Okay. Now we should see our period being 360, because it's in degrees. So if I zoom out, where is this? 360. negative 360, 720, negative 720, negative 1080, 1080. Okay, so we can make this be anything now. So say we want, here, let's make it so that we can just do, so 2 pi is a full circle, right? Or tau, whatever. Anyway, so let's say we want to make it, we want our unit to just be 9 units per circle, per full thing, right? So now we're going to get, where's it at? Oh, I saw them a second ago. Oh, this one, there we go. 9, 18, right? And here your base is 2.01, real close to 2.01. Your base, it's not E, it's really close to 2.01, right? What if, what we can do now is we can just set, so what happens if it's 3? What happens if our base is 3? What does our period look like? 5.719. It's going to be some irrational number, I'm pretty sure. Right. What if our base was pi? .489. That's weirdly close to 2e, isn't it? What is 2e? Interesting. Yeah, so I mean it could be anything, right? And it's different. Now your period changes as you move around. And at 1, something magical happens. Something truly magical happens. At 1, it doesn't make sense. And at 0, again, it doesn't make sense. So you have these two points here where it's just crazy, and negative values don't make sense. So, well, they sort of should. Anyway, I'm not going to argue that one right now. But, yeah, this is, I think, it shows us something far more interesting than this. It's also far more accurate. Because here, we're sort of pretending, because these are just dots. If this generalization were correct, these should be horizontal lines, because what he did is he took this point, just this vertical line, and he stretched that out horizontally and artificially made what is actually 2 pi into 2 pi I. So there are some mistakes here, I would say, and that is greatly misconstruing what's occurring here. But yeah, no, I just found, I saw that yesterday, and I was like, okay, I see what you're saying, but I think there's something missing here. So I spent some time trying to figure it out. Probably more time than it's worth, because nobody cares. But the point is, to me, that E isn't actually entirely fundamental to the way complex exponents work. It's nice because when you use E, the period is expressed in radians. That's why it's nice. But we don't have to express the period in radians. We can express it in anything we want. And when we do that, our base changes, and our units of angle change too, right? So we can we can look at it in a few different ways. We could look at it in what do we want our angular units to be? Do we want it to be radians, or do we want it to be degrees, or whatever? Or what do we want to use as our base? We don't have to use E. And if we use something else, well, what does our period look like? So what is our, and that's going to tell you what your units of angle are. So this is a more generally useful way of looking at it, I would say. Yeah. Anyway, there you go.